Hello, it's me, Chris. That's right, I am back. And in this video, I want to talk about dependency injection. Here are the topics that I would like to cover. I'd like to talk about dependency injection as a concept, sometimes also known as inversion of control. I want to talk about dependency injection frameworks, i.e. the implementation of the dependency injection concept. And I want to show you how to implement a dependency injection framework specifically in C# and in the Unity game engine. A few notes before we begin. All of the code that I'm going to be showing in this video is going to be pure C#. Even though I'm doing this in Unity, none of the code that I'll be showing today depends on Unity at all. So you're free to use this on any kind of C# project that you want. In the next video of this series, I am going to be showing Unity-specific code, but not today. The code will also be publicly available on GitHub. Links will be in the description, so feel free to browse it and use it however you see fit. Now, I don't necessarily recommend that you use this for your own production projects. I will be using this in my own projects, but if you want a production-ready framework, I strongly recommend that you take a look at IContainer, Inject, and other such frameworks that have been battle-tested for way longer than this one has. The main reason that I'm showing this in this video is for educational purposes. So, what is dependency injection? From hearing this term, you may be fooled into thinking that it's something really complicated. However, the concept of dependency injection is actually incredibly simple. If we take a look at the definition, all that it says is that an object or function receives other objects or functions that it requires, as opposed to creating them internally. So, what does that mean? If you have a class, like the one I have here, there's a car, the car needs an engine, and in the constructor, we instantiate the engine for it. If you compare this to this other version, there's also a car that needs an engine, but instead of instantiating the engine, we simply receive it as a constructor parameter. So when you turn this into this, you've just used dependency injection. Yes, it really is that simple. This really is one of those $1 million words for a 5-cent concept. Now, having said that, the way that dependency injection is implemented in practice usually involves the use of a dependency injection framework, and implementing one of those can be quite complicated. But, as we've just seen, you don't have to use a framework in order to use dependency injection. It's just that when working on projects of a certain size, it tends to be helpful. Moving on to the other term that I'd like to talk about, inversion of control. This is quite an interesting term because originally it had a different meaning. Well, it still retains its original meaning, but when Java and its DI frameworks gained popularity, the term became almost synonymous with dependency injection. And that new meaning is now, I would argue, a lot more well known on the internet than its original one. The original meaning of IOC, or inversion of control, has more to do with event-driven programming, where traditionally you would code the flow of your application yourself and then make calls to external APIs or frameworks to help with certain tasks. But with inversion of control, you would flip this around, where you would use an API or framework to control the flow of your own application, and then you'd provide the framework with event handlers or callbacks, which the framework would call for you at appropriate times. That's what the inversion meant in terms of inverting control, where you don't control your own application flow anymore, the framework does. But when dependency injection became popular, mainly through Java, the inversion of control started to mean a different thing. In this case, you're granting the framework control over the implementations of dependencies, rather than giving it control over the application flow. Let's talk about dependency injection frameworks a bit now. The way these frameworks usually work is by providing you with a container object. In the container, you register types or other objects, and then when you try to create new instances of any of the registered types, the container will automatically supply them with the dependencies that they need. That is, if those dependencies have also been registered. Let's see an example. You have a container, and even though I just said that usually you register objects in the container, actually most dependency injection frameworks typically have a level even above this that is called a builder. And in the builder is where you actually do your registrations. And the reason to do it like this is to make things a little bit more consistent and less error prone. You register everything in the builder, and then when you are done, you create a container from that, and the registrations in the container become read-only. So prevents you from accidentally deregistering things while the container is in use. So yeah, just makes things a little bit safer. So in this builder, we can register our car interface as a concrete car. And when registering, there's usually 3 types of lifetimes that you can pick from: singleton, scoped, and transient. Singleton means that there should only be one object of this type in this container. Scoped means that there will be one instance of the object per scope, and we're going to take a look at scopes a little bit later, so don't worry too much about that for now. And transient means that a new object of this type should be instantiated every single time it's requested. So for the car, let's say it's a singleton, and then we can register our engine interface as an engine concrete type. And let's say the engine is transient, so every single time an object requests an engine, a new one will be created. So from the builder, we can build our container. And now that we have the container, we can resolve an object of type iCar. And this should provide us with an object that is actually of our concrete type car. So if we do a check like this, this should return true. And not only have we created an object of our concrete type car, that object should also have an engine that is of our concrete type engine. So we can also do a check for it if we'd like. Since I'm in Unity, I've just converted this to a mono behavior for quick testing. Let's drag this into some random object in our scene, and let's play and see. In the console, it prints exactly what we expected. There we go. So now that we've seen at a very high level how a dependency injection framework typically works, let's have a look at how to implement our own from scratch. Let us start from the top down. First, we are going to need a builder. Let's put this in a nice namespace. The builder is going to hold our registrations. Let's make this a dictionary that is going to hold the abstract type on one side, and we can't directly make it a type here because we also need to hold information about the lifetime. So let's make a new struct called registration. We'll make it a struct. We'll make it a read-only struct, actually. We don't want to be changing any of this after it's instantiated. This is going to hold our lifetime. we also need to create that. This is an enum that is simply going to list singleton, scope, and transient. So lifetime. Let's make a constructor for this. And we also need a dictionary to hold already instantiated objects, because we might want to register objects that already exist that we have instantiated ourselves. For the registration functionality, we're going to have a few functions. I like to have these functions return the builder itself. That way you can chain them if you'd like, but you don't have to do this. So it's going to have one type on one side, which is going to be the base type, and then another type on the other side, which will be the derived type. This type here should not be an interface or an abstract type. You'd need to be able to instantiate it. And it's also going to take a lifetime parameter. And in order to make sure that the compiler enforces the relationship between the base and derived types, we can add a generic constraint where we say that derived needs to derive from base. So what we do with this is we simply add the type of base as the key in the dictionary, and as the value we have a new registration that takes the type of t derived and the lifetime, and then we return ourselves. We also want to provide the ability to register an already instantiated object. So we are just going to have a single generic type, and we are going to pass in an object of this type t, and we're going to say that t is not null. This is just a helpful generic constraint to increase the odds that we catch any null objects that are passed into this. It's not a 100% guarantee, but it's better than nothing. So when we pass an object like this, we're going to register in the objects dictionary, and the key is going to be its type, and the value is going to be the object itself. And for the registration, we are basically going to do the same thing. We'll just copy this line over here, and instead of t base, it's just t. And here we don't have a derived type, but we do have the object already, so we can get its actual type instead. And for the lifetime, if the object already exists, then the only lifetime that really makes sense is singleton. And one last registration method, just as a convenience, where in case we want to register just a type without necessarily having a base in the derived type, and this one is literally just going to call the first method we made, but with the same type on both generic parameters. And then the only thing that we need, after having all the registration methods, is to be able to build a container from this builder. So we don't even have a container class yet. Let's just make a container interface in the meantime. I know we're gonna want interfaces for all of these anyway, including for the builder. But for now, let's just make a container interface. It's not even going to have anything. Just make it an interface. So we need to place it in our namespace. Actually, we should do the same for the registration. and the lifetime as well. So back in our builder, give it a return type of IContainer, call it build. For now, we're just going to declare a container and assign it to null. When we have an actual container implementation, we should construct it here. And then at the end of the function, we return it. But before we do so, we should also do some validation. We should check for missing dependencies and check for circular dependencies as well. If any of these conditions is not validated properly, we should throw an exception. Before we move on to implementing the container, I just want to make an interface for the builder and add the relevant public methods to it. It should be placed in the same namespace as the rest of our stuff. So we're just going to place all of our public methods in there, including the build one. But instead of returning the builder concrete type, we should return the interface type. And in the builder class, we should implement the interface. We're going to say to implement the interface explicitly. Let's drag this all the way up here to the top. And yeah, that's basically exactly what I wanted it to do. I guess it got a bit confused on this one. Yeah, well, we just need to return the version that receives an object as a parameter. So if you are confused about this, these are explicit interface implementation. So basically what this means is if you have a variable that is of type builder, the concrete type, and you call the register methods, it's going to call these ones and return a concrete builder. But if you have a different variable that is just of type IBuilder, then it's going to call these ones instead and return an IBuilder. So you're not going to know necessarily what the underlying type is. You're just going to have access to the interface. So when you do an explicit interface implementation, it basically means that the methods that you've implemented that way are only going to be called when you are accessing the object as that interface. Moving on to the container implementation. We shall place it in our namespace as usual. Make it implement the container interface, even though it doesn't have anything yet. So the container also needs to hold dictionaries of objects and registrations. These are basically going to be copies or taken directly from the builder that created it. In addition to that, we also want it to hold a list of other containers. And in this case, I'm going to call it child scopes. So this is where the scoping that we briefly talked about earlier is going to come into play. Even though, if I'm honest, I don't really know how other dependency injection frameworks handle scoping. I don't know if the way that I ended up doing is the best or not, but it seemed okay to me, and it seemed like a useful feature to have, so I went with it. So we also want to hold a reference to our parent container. But in this case, I'm going to make it public, but read-only. That way nobody can change it except us in our own constructor. I also want to expose the child scopes list to any exterior access, but I don't want, once again, for it to be changed from that. I just want to expose it as a read-only variable. So I'm going to use the IReadOnly list interface and also set the variable itself as read-only. So doing it like this, nothing from the outside can change this variable itself because it's read-only, and also nothing can change the list because it's a read-only list and not a concrete list. In the constructor, we are going to receive the objects and registrations dictionaries that we need. So we actually don't want to create new instances of them here. And actually, let's do the same thing for the child scopes list to make it a bit nicer and more consistent. Beyond receiving the objects and registration dictionaries, let's also make a different constructor that receives another container as a parent. And let's have the second one call the first one, passing in objects and registrations, but not the parent. So this one will just set parent to the received one, and this one can set the objects dictionary and the registration dictionary to the ones that were received as well. And we also need to assign the child scopes lists. So basically we are creating the child scopes private variable as a list, and then we're immediately assigning it to the public child scopes variable as a read-only list. And because list implements a read-only list, it's simply a matter of assigning the variable to the other, and C# casts it for us automatically. Oh yeah, and when we assign the container as a parent, we also need to go into the parent container and add ourselves as a child. Okay, now that we have our objects, registrations, and child and parent scopes all set up, we can start looking into implementing object and type resolution functions. So let's begin by mapping out the resolution functions that we would like to have. Let's say we want to resolve objects of a specific type. So we want the container to look for a registered object of type T and give us the actual instance of that object. That's one of the resolution functions we want. Let's take a look at the other ones first before we start implementing them. We can also, let's remove this from here, we can also ask for a generic version of the same function basically, but instead of having the type, we may have just the system type, and we don't know what the actual type of it is, so we're just returning a generic object. We can also have try resolve style functions for the same things. In this case, it returns the object as an out parameter, and it returns either true or false in the body of the method. So we don't really know the type of this T object here. It's not necessarily a reference type, so we should use default instead. However, when we do that, it's giving me a warning. And the reason for this warning is because I am using nullable reference types in my project. That's something that you can enable manually in Unity. It's a, let's say, relatively new feature of C#. I'm not going to cover in this video how to enable it because that's a little bit outside the scope of the video, but surely I'm going to have another video soon explaining how that's done. So in order to fix this warning, we can actually add this attribute. We need to add the namespace for it as well. This basically just tells the compiler and the static analyzer that the value of this out variable may be null when the function returns false. So if the object assignment is in the same branch where you return false, it's not going to give you any warnings. But if it was returning true, then it would be giving you a different warning because, yeah, object must have a non-null value when exiting with true. Yeah, that's pretty nice. I'd recommend you give it a shot enabling it if you're interested in this. So same as we did above, we don't just want the try resolve version that receives a generic T, we also want the one that receives the type as a system type object and returns a generic C# object as well. So instead of returning object, we return bool, and here we return the object as an out variable. We do the same thing for the out parameter, and let's also assign it to default and return false for now. And let's copy paste this whole thing and do more or less the same thing but for types. So instead of resolving objects, now we're going to try and resolve types. So when asking for an object with a generic parameter, we can't simply return an object of that type. We actually need to return an object of system type. Same thing here. We ask for one type and we get another in return. And the same thing for all the other functions as well. Okay, so now how do we actually implement these functions? Let's start from the bottom here. And for the try resolve type, we are going to do a for loop, not on an I variable. We're going to do it on containers. So the first container starts as this. Then we keep looping as long as the container isn't null, and every iteration of the loop, we set the container to its parent. And by the way, we need the question mark over here, because this signifies that we are explicitly allowing this variable to have null values. And if you might remember, when we declared the parent for the container, we also declared it with a question mark, like once again saying that we are explicitly allowing it to have null values. Because, yeah, you might create containers that don't have parents, so it's not always guaranteed for there to be a parent. So yeah, here we start at the current container and we keep going up the chain until we either find the type that we are looking for, or we don't, and in that case we return false. So we are going to check if the container has any registrations of the type that we asked for. So this returns a registration struct. So here we just assign the resolved type to the type that is stored in the registration variable. So if we found the registration for this type, we return true, we succeeded. If we went all the way to the end of the loop, we went through all the registrations in this container, all the registrations in all the parents, and we still couldn't find anything. That means the resolved type does not exist. We don't have any registrations of this type, so we just return false. So now that we have this last function implemented, implementing the other ones becomes pretty much trivial. So for the try resolve type with a generic T parameter, we simply return the try resolve type that doesn't have a generic parameter, that takes a type as an argument instead. We pass type of T as that argument, and for the out parameter, we assign it to the resolved type variable. For the resolve type, not a try resolve type, so it doesn't return Boolean, returns the type directly, we want to check the try resolve type, and if that is successful, we just return the resolved type. If it's not successful, we want to throw an exception. We can use string interpolation here to print out a nicely formatted exception message. The resolved type variable also needs to be a nullable reference to be consistent with the maybe null when attributes. And for the resolved type with a generic t parameter, we just return the resolve type with a non-generic parameter, passing in the type of t. For a try resolve object, the idea is going to be very similar to the try resolve type. We need to do a for loop. So let's just copy and paste that into here, and we can change this variable to be object, but the logic in the inner if statement is going to be a little bit different. So we still need to get the registrations, but here the object is actually going to be returned or instantiated differently depending on the lifetime of the registration. So we are going to get the lifetime of the registration, and we're going to do one of those fancy new switch statements. We can even ask it to implement all of the cases for us, including the default case. So for the default case, we are going to throw a not implemented exception, but we're going to write a nicer message for it. Now, depending on the lifetime of the registration, we're going to have to create or get it in different ways. So if it's a singleton, we want to check if it exists in the container that actually has the registration. If it's scoped, we want to check in the current container, even if the container that has the registration is a parent of it. This means that even if the current container doesn't directly have a registration for this object, if one of its parents does, that should still be allowed. And if it's transient, we want to always create a new instance of that object. So for the singleton and scoped cases, we're going to need a function called something like get or create object. And this function is going to receive a type as the key and a resolved type, or in this case, the registration type, as the value. This will be the actual concrete type of the object to instantiate in case it doesn't exist. We want to use this, both of these cases, but we don't have this function yet, so let's create it real quick. Creating it down at the bottom as a private function. This function checks if the object exists in the objects dictionary, passing in the type variable as the key. So if this object doesn't exist, this check is negated here. If it doesn't exist, we want to create a new instance of it and assign it. But we also don't know how to create objects yet. Let's leave it blank for now. And if it does exist, we just return it. So in order to create objects, let's make yet another function, and let's call it create and inject, because we don't want to just create the object. We also want to inject it with all the dependencies that it requires. But since we don't know how to do that yet, let's just return null for now. And here we call this function, passing in the resolved type. So going back up to the resolve object function, we have the singleton and scoped cases solved. And for the transient case, we just always want to call the create and inject function. And here, let's actually remove the this keyword because it's not really required. Additionally, we also need to make sure that we return true in the case that we did find the registration. Just like with the previous try-resolve type function, now that we have the try-resolve object function, implementing the other ones is trivial. For the try-resolve object with the generic parameter, we should be able to simply return the try-resolve object with the non-generic parameter. Well, almost, but let's start with this. So we pass in the type of t as the first parameter, and we want to try to assign the second parameter into our out object parameter. However, we get an error here because here we expect something of type t, but this function returns an object instead. So we need to write just a little bit more code, but not that much. So we need to put this inside an if statement. If the non-generic try-resolve object function actually returns true, then we can grab the object that it returned and assign it to our object of type t by casting it. Because at this point, we know for sure that the type is compatible, and we return true in this case. Otherwise, we have to assign our object to default and return false. For the resolve object function, we will check the try resolve object return the object if this was successful. Otherwise, we want to throw an exception. And for the resolve object with the generic t parameter, we simply return the other one while casting it to t and passing type of t as the function parameter. Alright, so now the only thing that we are missing here is creating and injecting objects. However, before moving on to that part, I want to make this a little bit more tidy by completing the interface for it. So in the IContainer interface, I actually want to split it into several different interfaces. So let's take a look at the interfaces that we could extract from here. I want to split it into an type resolver interface and an object resolver interface. And as you may expect, in the type resolver interface, I want to add all of the functions that have to do with type resolution, and in the object resolver interface, all of the functions that have to do with object resolution. We should place these in our namespace. We're just going to come over to our container implementation and copy the relevant function headers to each of the interfaces. And for the container interface, we'll just make it implement the other two interfaces. Additionally, I want to expose in the interface the parent container and all of the child containers. Now we need to figure out how to create and inject dependencies on objects. As you might have guessed, the most straightforward way to do that is through reflection. So let's create a helper class that I'm going to call Reflection Injector. And the idea is that maybe in the future we could implement different versions of this class that don't use reflection to figure out how to create and inject dependencies into objects, maybe they use source code generation to generate all of the source code at compile time, and then at runtime you don't have to use reflection. But for now, let's do the reflection implementation. And let's actually make yet another helper class that I'm going to call a reflection cache, because reflection can be a bit heavy. If we can cache and reuse the results of processing a class with reflection, we should probably do that. In the reflection cache, I'm going to want to create a nested class here called injection info, and this is going to store all of the dependency information for a particular class, namely constructors, constructor parameters, fields, properties, methods, and method parameters. Additionally, just as a convenience, we will also add a final read-only list that stores all of the dependencies. And in order to make this not complain, we need to create a constructor for it that assigns all of the read-only list fields. To store all of this information, we're going to create a dictionary that stores a type as a key and as the value the injection info for that type. Let's make a public method called getInfo that returns an injection info for a requested type. And let's also create another function called processType that will generate the injection info for a type if we don't already have it. First thing that we need is to get the constructor info. But a class could have multiple constructors. So how do we know which one to pick for the injection process? For that, let's create a new class that we're going to call Inject attribute. And this, as the name implies, is going to be an attribute that the user can add to their own constructors, fields, or methods in order to mark them as an injectable member. That means our reflection cache and reflection injector will use that attribute to determine which fields, properties, methods, and constructors to use for injection. So this class needs to extend from the system attribute type. It's going to be an empty class, but itself is going to have an attribute called attribute usage, where we can specify multiple different targets, meaning different members that it can be used on. So we want this to be able to decorate fields, properties, methods, constructors, and even classes themselves. Being able to decorate classes here is not strictly necessary, but it may be helpful for example, code generation, to more easily find the classes that need code generated for them. We are not going to allow multiple attributes to be used for the same member, but we do allow it to be inherited. Back in the reflection cache, now we can properly implement the getInject constructor method. So the first thing that we're going to do is we will get all of the constructors for the type. And for binding flags, let's say we want public, non-public, and instance. Let's actually extract this as a constant variable. And simply call it flags. We get all of the constructors. If there's only one, then we can simply return that because there's no other choice. If there's more than one, we loop through all of the constructors and we check if the constructor is decorated with the Inject attribute. And we return that one if it is. If there were no constructors, or there were multiple but none of them had the Inject attribute defined, then we can't really be sure which one we should use, so we'll just return null in that case. Let's also extract this into a local variable because we are going to need to reuse it a few times. Class variable, I mean. Let's make it static and read-only. After getting the constructor, we need to extract the constructor parameters. Let's actually call this function getConstructorParamTypes to be more in line with what it actually does. And let's make it accept a null constructor. So if the constructor is actually null, then we simply return an empty array of types. Otherwise, we need to get all of the parameter infos and then from those extract all of the types. That means we need to allocate an array of the same size. So if the parameters array is actually empty, because it could be a parameterless constructor, then the constructor param types will also be an empty array of types. Otherwise, we instantiate a new array of the correct length. Then we iterate through all of the parameters, assigning the type of each to the constructor parameters array. And we return the constructor parameters array when we're done. Now we need to extract the fields, properties, and methods that we need to inject. And which ones are those, you may ask? Well, all of the ones that are decorated with our Inject attribute. In order to do that, we are going to use some helper methods that I've already created, which I'm not going to go into a lot of detail in the current video because they fall a little bit outside of the scope, but all of the code will be publicly available on GitHub when this video comes out, so you're free to check it out for yourselves. But I can briefly show a high-level overview of what these do. The main reason for having these helper methods is because, as you may read here in the comment, C# doesn't give you base class private members, even when you use binding flags non-public. You still have to manually search all of the base classes in order to find them. So we add the declared only flag to our requested binding flags. This just prevents some duplication, although not all. And then we iterate through the type and all of its base types as well until it doesn't have a base type anymore. We get all of the fields in each of those types and check if the attribute is defined. We also add the type to a provided list. This way the user can potentially reuse the same list and not have to allocate new ones every time, reducing memory pressure. For properties and methods, the process is very, very similar with an additional deduplication step, because both properties and methods that are inherited have some tricky cases where getting them through reflection like this can give you the same one multiple times. It's a bit of an unfortunate situation because if you don't search the base classes like this, you won't be able to find all of the private properties and methods, but if you do, then you'll have duplicates, and it's a little bit tricky to get rid of them. But for my testing, this does the job. Now, you could argue that for dependency injection, we shouldn't even be caring about private members. We should only be injecting public members, and I think that's a fair argument to make. But I needed this code for other things where I do need to find private members. Because I had already made this, I just decided to use it, so let's stick with this for now. Coming back to the reflection cache, now that we have extracted our methods that we need to inject, we also need to extract their parameters. For this, we will make yet another function called getMethodParamTypes. We will pass in the methods, and this should return something like an IReadOnly list of IReadOnly lists of type. Let's create that function further down. I'm now just realizing, actually, that the methods that we've previously implemented can be marked as static. This makes it slightly safer, because we enforce the fact that we are not using any instance class variables. This is simply what sometimes is called a pure function, meaning it simply receives inputs, processes those inputs, and returns something based on that. Doesn't keep or alter any state or anything like that. So for the getMethodParamTypes, we will take some clues from the constructor parameters that we've previously implemented. So we'll need to declare a new array of arrays to return. And we'll check our methods. If the list of methods is empty, we will simply return an empty array. But if it's not empty, then we need to instantiate a new one with methods.count as its size. This is just for the top level array. Now we need to take care of the inner arrays. So for each of the methods that we have, we will grab all of the parameters, and then we will assign the corresponding method parameters. Once again, we will check if there are any params to begin with. If there aren't, we will return an empty array, and if there are, we will allocate a new array of the same length, and then we navigate through all of the individual parameters. This variable needs to have a different name, and we will assign the actual individual parameter as the parameter type. And when we are done with all of this, we simply return the array that we allocated at the top here. And by the way, if you are finding it strange, the usage of all of these array.empty calls, this just means that we are returning an empty array, so not null. That helps for code cleanliness because we avoid having to do null checks whenever we need to use the data returned by this method, or any other one of the methods we've made. But it also reduces allocations because we're not allocating a new array with size 0 every time. It's always going to be the same object that is shared. So it reduces memory pressure a bit. So we have almost everything that we need to create our injection info from processing a type. The only thing we're missing is this last convenience list that gathers all of the individual types from all of the members that we processed. So let's take care of that now. Let's first of all figure out the size of the list that we need to allocate to grab all of the individual types that are dependencies of this type. So that's going to be the number of constructor parameters plus the number of fields plus the number of properties plus the number of method parameters in each method. So now we need to iterate through this list here, and we will say that count is plus equals the number of parameters in each method. So now we can allocate a list with capacity count, and we will make one last method called getAllDependencies. This will receive all of the previous lists that we've built, so constructors, fields, properties, methods, and method parameters. And we will pass in our dependencies list as the last argument as the list to be filled. In this case, we don't allocate this as an array like we did for method parameters with a fixed size, because even though we tried to estimate the size of it by doing this, it's not actually guaranteed that this will be the exact number of dependencies, because some of these might be duplicated between fields, properties, methods. Some of those types may be the same type. We don't know yet until we've processed them. So we allocate the list with as much space as it might need, but then it may end up being slightly smaller. Okay, so let's implement this function. Let's scroll all the way down to the bottom. Once again, let's make it static. This one is going to be void, because it's not going to be returning anything, it's just going to be filling a list that we pass as argument. And this one, just because I know it's going to receive quite a few parameters, let's declare it like this. I don't usually like to do this for readability purposes, but and lastly, our list to fill. So here it's going to be relatively simple, although a little bit repetitive. We are just going to iterate through each one of these lists and assign the type to the all dependencies list. My bad, this is not an iRead-only list, this is just a regular iList, because it needs to be writable. So we add it to the list, but like I said before, some of these types could be duplicated, and we don't want that here. So we're gonna have to do a contains check first. So if it doesn't contain the type, then it gets added. I don't love having to do a contains on a list, because this is a ON operation, meaning it's going to need to iterate through the entire list to check for duplicates every time we do this. So we're essentially iterating this list many times over the course of this method. But based on things that we're going to see later, it's very convenient to have this as an actual list and not a hash set or something like that. So yeah, I'm going to take the hit to performance here for convenience later. And we can essentially just copy paste this a bunch of times and change the variables here. So for one, it's going to be fields and gets the field type. The other one is going to be properties and gets the property type. And for the methods, it's going to be a little bit more involved. We are going to need a nested loop. Alright, I've just realized we don't actually need to pass in the methods themselves, because the method parameters already has all the information that we need. So we can go back to our function that we were building, the process type, and remove the methods argument as well. And now that we are done with all of this, we just need to actually create the instance of the injection info that we were doing all of this work for. And we will pass the constructor parameters, the fields. But here we want to actually turn this into an array and make a copy of it, because in just a second we're going to make some small changes to these lists where we actually reuse the lists to avoid so many allocations. So we are going to pass in the properties and we'll do the same thing, turn it into an array. Same thing for methods. Method params and the all dependencies list as well. Once again, making a copy of it, turning it into an array. And after building our injection info object, we can actually return it finally. Alright, so for these lists, to try and avoid so many allocations, we are actually going to replace all of the usages of the regular list class with something else. We are going to use a pooled list, and this is another utility class that I've already implemented, like the type extensions, which I'm not going to be covering in detail in this video. But like I said previously, all of this code is going to be publicly available, so you're free to check it out and use it. But essentially, what a pooled list is almost an exact copy of the regular list class, but internally, it uses an array pool for the arrays. So whenever the internal array of the list needs to be resized, instead of allocating a completely new array, it simply grabs one from the pool, so they can also be reused. And on top of that, the pooled list itself is also pooled, so you can rent them just like you do for the arrays in the array pool. In case you don't know about the array pool class, by the way, this is a relatively new thing introduced by Microsoft, and I would definitely recommend you read up on it because it's quite interesting and it has very useful use cases. So yeah, the pooled list itself is pooled, and internally it uses pooled arrays as well in an effort to try and reduce allocations. And when I say that the pooled list is essentially a copy of the regular list class, I do mean that quite literally, because what I did to implement it was literally coming over to Microsoft's official .NET source code, which you can find at this link, source.net. Kind of a weird address to say, but yeah, you can literally come over here, search for any class that comes included with the C# language, and you can browse its source code. So I quite literally copy-pasted this code, changing the names of some variables here and there, and then edited the internal items array that you see here to use an array pool instead. And it also has an implementation of the IDisposable using pattern. So basically, you can simply preface the variable declaration with the using keyword. And what this means is, as soon as this variable goes out of scope, in this case it means as soon as this method ends, when it returns, this variable goes out of scope, it's no longer used, and the C# compiler is going to call automatically for you the dispose method from the IDisposable interface. So in order to do this, you basically just have to implement IDisposable, and yeah, implement your dispose method, and that's going to allow you to do this. So we're going to do the same thing for properties, and for methods. And also, actually, for the all dependencies list as well. And in the case where you call rent with a count property, it's going to behave identical to the array pool rent, where the count here just means the minimum size that it's going to have. It could actually give you a bigger list than you asked for, but that's just how the implementation of the array pool works. So, and now that we are using these lists that are essentially going to be reused many times over, now you can understand why we actually need to make copies of them when we instantiate the injection info object. Otherwise, we would have lists with completely different data than we actually intended. Yeah, we don't need to do that for the constructor parameters list because we are instantiating it manually. And the same thing for the method parameters. These both get instantiated inside their own methods. But other than that, we actually need to make copies of our data. Before we move on to the Reflection Injector, I just want to make a small change here that would allow the reflection cache to be used in a multi-threaded environment. What we're going to do is create two additional methods. One that we will call tryGetFromCache. This will receive essentially the same parameters as the tryGet value. So we'll have a type as the key and an injection info as the value. And this method will lock our cache and return the tryGet value call. And then the second method that we need is an add-to-cache. It is going to have the same parameters, except the injection info is not an out parameter. And it's going to do a similar process. It will lock the cache and assign the injection info to the type. Now in the getInfo function, instead of calling tryGetValue from the dictionary directly, we will call our tryGetFromCache method that we just made, and inside the if statement, we will not assign the processed info directly either. We will save it in this variable, and then we will call add-to-cache afterwards. Doing it this way attempts to reduce the amount of time that the dictionary is locked. We only lock it at the exact moment that we are trying to retrieve something from the dictionary and at the exact moment that we are trying to assign something into it. But whenever we are processing the type, because this is going to probably be the heavier operation, while we are processing the type, it is not going to be locked. Even with doing it like this, you may still be thinking, well, if we want to make things multi-threaded, it's silly to use a regular dictionary. We should instead use a concurrent dictionary. And you may be right, although I do have a reason why I'm still choosing to use a regular dictionary with locks instead of a concurrent dictionary. And it is as follows. As you may have noticed, I am using this in Unity. Now, most of the code that we've shown so far, actually all of the code that we've shown so far, does not require Unity at all. It could be used in any C# project, but my main use case for this is Unity. And as you may or may not know, Unity tends to be, for the most part, single-threaded. That doesn't mean that you can't spawn your own threads and do things multi-threaded yourself. And especially when you have code like this that is just pure C#, you could very well do that. It's just that when you have to mix regular C# code with engine calls, the engine code, for the vast majority of the time, cannot be multi-threaded. So my guess is that this code will, for the most part, be called in single-threaded scenarios or scenarios with a very small number of threads. And in those cases, as far as I know, I could be wrong, but as far as I know, a dictionary with locks is probably still faster than a concurrent dictionary when you have very few threads or just a single thread. As soon as you start getting into a decent number or a high number of threads, then concurrent dictionary is definitely faster. But my expectation is that this won't be used in those scenarios that much, so that's the reasoning that I'm going with. Feel free to disagree in the comments. As long as you're not rude, all of those disagreements are extremely welcome, and if you are rude, you're just gonna get banned. Anyway, with all of this done, now we can go back to the Reflection Injector and actually implement that. Here we will declare a variable of type Reflection Cache. We haven't been doing all of this work for nothing. We actually need to use it. And we shall also declare a variable of yet another one of the utility classes. In this case, it's an exact size array pool of object. We'll use this in order to reuse the arrays that we will need for injecting constructors and methods. And once again, apologies for using so many utility classes that I'm not showing in detail. This is an implementation of array pool that returns arrays of the exact size that you requested instead of returning an array that may be bigger than what you requested. And if you're not sure why we need arrays of exact size, it will become clear in a second. So let's declare a constructor for this class. And for the parameters of this constructor, we will pass an optional reflection cache in case we want to reuse an existing one that we may have. And we will also pass an optional array pool for the exact same reason. Here we assign our class member reflection cache either to the reflection cache that we passed in as a parameter if it exists, or if it doesn't exist, we create a new one. And we shall do the exact same thing for the array pool, but instead of instantiating a new one, we will use the shared instance. So for the injector, there's essentially two things that we need. We will need to be able to create objects where we specify a type, and we also need to specify an object resolver. This is the type of the object that we want to instantiate. It needs to be a concrete type, cannot be abstract. And then the object resolver is used to resolve the parameters of the constructor. The parameters of the constructor of this concrete object can be abstract or interfaces or anything else, and we need a way to resolve them to the actual real object that we need. So we'll need to grab the injection info of the type that we passed in. We will use our reflection cache to do it. And now we need to take a look at the constructor of this type. We need to check if it even has a constructor to begin with, and if it does, we need to grab some of its information in order to actually construct an object of this type. Let's save the parameters length. We will grab this from our constructor params list. We will get an array of objects that will be the actual instances that we need to pass into the constructor. And we will grab this array from the array pool. We shall rent an array of this length from the array pool, and now it may start to become clearer why we need the array pool to return objects of exact sizes, because in order to build an object via reflection with a constructor, the objects array that is passed as the parameters of that constructor needs to be the exact size. So we iterate through all the parameters, grab their types, and then use the object resolver to give us the object that is registered for that type. After fetching all of the objects that the constructor requires, we instantiate the actual object that we want to return by getting the constructor from the injection info and simply invoking it with the constructor params that we just gathered. When we are done with this, we need to return our constructor params array to the array pool, and we will set the clear array boolean to true so that the objects array can be safely reused later without any lingering objects. And finally, we return the object that we just created. In the case that we actually didn't find a constructor, we will check if the type is abstract or not. If it is not abstract, even though it doesn't have a constructor, it means that there's still a not very well-known way to instantiate an object of this type, and it is by using formatter services get an initialized object. And you pass in the type that you want, and this should give you an object with all fields set to their defaults, even if it doesn't have a constructor. And in the last case, that means the object is actually abstract. That means it's simply not possible to create an instance of it. So we'll just throw an exception saying cannot create an object of this type. And let's just quickly fix a mistake here. This resolve object call shouldn't be receiving the type variable here, it should be receiving the item inside the loop. The second thing we need for the reflection injector is a method to inject objects. This one will have as parameters an object and also an object resolver. For the first method that we made here, it just creates an object by using the constructor. Basically just doing the constructor injection part of dependency injection. For the inject function, we are doing injection on everything else. So that's fields, properties, and methods. First, we need to know what the actual type of the object that we passed in is. So we will call the getType function on it, and then we will need to get the injection info for that type. Now that we have this, we can iterate through all of the fields and call the setValueReflection method, passing in the actual object that this field belongs to, and passing in the object that should be here based on what is registered in the object resolver. We shall do the same thing for properties. And we will do something similar for methods, but we need a little bit more work because methods have multiple parameters themselves. So we iterate through each method info. We grab the list of parameters for that method, and then we iterate those parameters, and we get the objects that are registered in the object resolver for each of those parameters. We need to store these somewhere, so let's actually once again Just like we did here for the constructor, we will rent an array of exact size from the array pool. Should be the same size as the parameter list. Instead of calling it constructor parameters, it should be method parameters. And so we assign the resolved object to the corresponding index in the method parameters array. And when we've gathered all of these, we can simply invoke the method from the method info, passing in our object and the correct array of parameters. Once again, at the end, I'll just copy paste this from up here. We need to clear and return the array to the pool. Chris, from the future here, there's actually a mistake. The variable to iterate the param types here should not be I, but should be j instead. So that should be it. This should be correctly injecting all of the fields, properties, and methods of the object that we passed in. We are almost done here so that we can go back to the container and finish implementing it. But before we do that, I want to create an interface for the injector, because I want us to be able to create different types of injectors in the future, and I don't want the container to be tied specifically to the reflection injector. Like I said before, one of the future goals of this is going to be to introduce code generation, such that all of the code required to instantiate and inject objects is actually created at compile time, and we don't have to rely on reflection at runtime. So let's make an interface for this. Just waiting for it to compile. So here, let's create a IInjector interface. Place it under our namespace. Remove the unnecessary Unity engine imports. And this interface is basically just going to contain the method signatures for the public methods that we just made in the Reflection Injector. I actually want to add one more function here to this interface that we are not using right now, but it's going to come in handy very soon. And this one is going to return a read-only list. It's going to be called getDependencies. So you're going to be passing in a type and then asking it to give you all of the dependencies required by that type. So let's make our Reflection Injector implement this interface, and it's going to complain because it doesn't actually have this last function that we just added. And this one is trivial to do. This one we just return the all dependencies list from the injection info that we can get from the reflection cache. And now we finally have what we needed to complete the container class. So here, in this create and inject object method that we didn't know how to implement at the time, now we do know how to do it. We are going to create an object from the reflection injector, and we actually need to declare it first, so let's go back up here and declare a variable of type IInjector. And because we want this to be an interface and not a concrete type, we shouldn't be tying the container class to a specific type of injector, so we don't want to do something like this. Yeah, we don't want to do this. So instead, we will follow the principles of dependency injection ourselves here, and we will simply have this be passed in via a parameter in the constructor. And as such, the injector will be assigned from someone else outside. And in the second method, we actually don't want to explicitly pass an injector, because this container is already going to be scoped to another parent container. The parent should already have an injector of its own, and the injector of the child should be the same one. So when this constructor calls the other constructor, we just pass in the injector belonging to the parent. Okay, going back down. So the object that we are trying to create, we will simply call the createObject function from the injector, passing in the resolved type, and we pass ourselves as the object resolver. And as the name of this function indicates, we don't just want to create the object, we also want to inject it. So we are just going to do injector.inject, and we pass in the object that we just created. We once again pass ourselves as a resolver, and then finally return the object and with all of its dependencies in place. Alright, we are almost done with everything we need to have a pretty robust dependency injection system. Now we just need to come back again to the builder and finish actually building the container. So now we know all of the parameters that a container requires. It needs one of two things. Either it needs a parent and the objects and registrations dictionaries, or a standalone injector, and again, the objects and registrations. So when we actually create a new builder, it should already be aware whether or not it's a builder for a standalone container or a container that has a parent. So up here, let's declare variables for that. So one of the possible variables that we are going to need is a parent variable, but this one is not required necessarily. Some containers don't have parents, so we're going to declare it as nullable. And the other variable is the injector, and this one is not optional. All containers need an injector. Sometimes it's the injector belonging to the parent, but either way, it always has to exist. Let's make a constructor for the builder. Actually, two constructors. One of them won't have any parameters, and it is just going to assign the injector to a new instance of the Reflection Injector that we just made. And the other constructor will receive a parent. We should assign the parent class variable to this one, and the injector to the parent's injector. But here, when we instantiate a new Reflection Injector, you may remember that this constructor can actually receive a reflection cache as a parameter in order for us to share the same reflection cache between multiple injectors. And that's precisely what I would like to do here. So in this class, I'm actually going to declare a static variable, read-only as well, of type reflection cache. And as such, whenever we instantiate a new Reflection Injector, I'm just going to pass in this static one, and being static, that means it's shared between all instances of Builder, so there's only ever going to be one. So it's going to be shared between all injectors, so we don't need to process and cache all of the types multiple times. Even this Reflection Injector itself could maybe be a static variable, but we will leave it like this for now. And now that we have our injectors and our parents set up in the builder constructor, we can actually instantiate our containers properly. So we will check if the parent is not null, And in that case, we'll create a container using the constructor that takes in a parent. It should also take in the objects and registrations dictionary. But if the parent is null, then we will instantiate the container by passing in the injector instead. And also, of course, the objects and registrations. However, we can't simply pass the objects and registrations dictionaries directly into the container, because they belong to the builder. And the user of this builder may call the build function and then keep registering yet more things into those same dictionaries. And we said earlier that we want our container registrations to be read-only. That means after the container is built, no more changes should be allowed to the registrations that it has. So in order to prevent that, we can simply create copies of these dictionaries. So here, instead of using the original dictionaries directly, we create copies of them, and we use those copies to build our container. Before we tackle the validation, I also want to register the container in its own objects and registrations dictionaries. So this is going to be the only exception to what I just said about these being read-only after container creation. You would need to call something like this, but we can't call our own register function directly because, again, that one is operating on the class members, objects and registrations. And in this current situation, we actually want to register to the copies that we just made. So we don't really have a straightforward way to do that right now. So what we're going to do is actually copy the existing register function that we have. We will make it private and static. We will make it return void. We don't need to return the builder here. And here we have to receive the dictionaries that we want to use. But otherwise, the registration code is going to be the exact same. So here we don't call the regular register function. We call the one that we just created by passing in the correct arguments. So beyond registering the container as itself, we also want to register it as an object resolver and as a type resolver. So here I don't like that VS Code is suggesting that the name can be simplified, because yeah, it could definitely, it's already of type IContainer. So I'm actually going to declare this as the concrete type, not the interface, so that the registrations remain explicit and actually look like it's done on purpose, because it is. And to finish all of this up, we are going to create one last class. We are going to call it Dependency Validator. This is going to be a static class, and it's going to define a few things. First off, we'll create a struct that we'll simply call data. So this will be the data that is returned after validating dependencies. And this data will include a read-only dictionary with a type as the key and a read-only list as the value. And this list will also be a list of types. We declare this as nullable, and we call it missing dependencies. So this means that after validating dependencies of a container, if they have any missing dependencies, then this dictionary will not be null, and it will contain all of the dependencies that are missing. And we will do almost the exact same thing, but instead of missing dependencies, these ones are going to be circular dependencies. We should make a constructor for this, So now we have the structure of the data that we need to return here. And this validator is going to do one main thing that we will simply call validate. Surprise, surprise. This will need a type resolver. Let's just simply call it resolver. It is going to need an injector and two read-only dictionaries. One for objects and another for registrations. For this function, we will need to figure out for each type if it has any missing dependencies and which dependencies those are, and also if it has any circular dependencies and which those are. We declare both of these as nullable because if the validation is successful and there are no missing or circular dependencies, we don't want to allocate any unnecessary memory. For finding circular dependencies, we also need to store a list of the types that we have already visited. This is needed because the circular dependency check is recursive. Can mean that there's an endless loop of dependencies and we need to keep track of the ones we've already seen so that we don't get stuck in that loop. We need to iterate through all registered types, and for each resolved type we will implement two additional methods, one for checking if it has a missing dependency and another one for checking if it has circular dependencies. If either of these cases are true, we can allocate the corresponding dictionary if it doesn't exist and assign either the list of missing dependencies or the list of circular dependencies. We haven't built those lists yet. That's going to come out of the implementation of the circular and missing dependency checks, so let's do that now. Both of these functions will be static as well. And for has missing dependency, it's going to receive the resolved type, the type resolver, the injector, and it will have an out parameter for the list of missing dependencies. We'll need a new list to store the possible missing types. We'll declare it as nullable as well, for the same reason as above. If we actually didn't find any missing dependencies, then we don't need to allocate any unnecessary memory. And here's where storing all the dependencies for a type in a centralized place comes in handy. So that's from the injector.getDependencies function, which simply maps to the all dependencies list in the injection info. With this, we can easily get all of the dependencies for a particular type, and it really helps us to check if any of the registered dependencies in the resolver are missing or circular. So we iterate through all of the dependencies. We check if the resolver can resolve that dependency, and we discard the out parameter because we don't need it here. If the dependency could not be resolved, then we definitely have a missing dependency. We can allocate the list if it didn't exist yet, and add the dependency that we were currently iterating on to that list. At the end, we can assign to the out parameter, depending on if we found any missing dependencies or not. We can assign the missing types list directly, or if we didn't find anything, we can use the array empty construct to avoid unnecessary allocations. and we can check whether or not there were actually any missing dependencies to return true or false. We can go back up and finish the missing dependencies part of the validate method. What this means here is that for any given type, if any of the dependencies that it needs are missing, we are going to have an entry in the dictionary that lists all of the missing dependencies, because they could be one or more. To check for circular dependencies, the parameters will be similar, not exactly the same. Instead of checking the resolver, we will instead check the objects and registrations dictionaries directly. The last parameter is also not an out variable this time, and we will simply receive the visited types list as a regular IList, not read-only, because we need to be allowed to write to it. The check for circular dependencies is going to be recursive. And as with all recursive methods, we need a stop condition. That is going to be checking if the visited types already contains the type that we are checking for, and if it does, we know there's a circular dependency, and we stop checking. Just as convenience, we also add the type again at the end, just so that we are sure where the circular dependency is, because this way the list will always end with the type that's causing the circular dependency. We also want this to be a list and not a hash set, even though that makes the contains check much slower, but we need to preserve order, because we definitely need to know the exact path that led to the circular dependency. Once again, we fetch all dependencies from the injector, and we iterate over them. In order to check if this is a circular dependency, we will see if this type is registered in the registrations dictionary, and if it is, we will call recursively the hasCircularDependency method once again, this time with the resolved type, and we return true if this call returns true as well. There's an additional check we need to do in the outer if, which is checking if this type is not contained in the objects dictionary, because if we already have a concrete instance of an object that corresponds to the requested dependency, then it's not possible for it to be circular, because the object already exists. By the end of everything, we need to remove the last element from visited types, because we added it all the way up here, and if we get to the end of the method and we actually didn't find a circular dependency for this particular type, then it doesn't count, so we need to remove it, and we return false. With this, we can go back up and finish the validate function. When assigning the value for the circular dictionary, we actually need to copy the visited types, since we are reusing this list for multiple checks. For each iteration of this loop, we also need to clear the visited types list, because this list is only valid for each individual iteration. It should not keep the same values across multiple iterations. And by the end of the whole method, we simply need to create our data struct and return it. Going back to the builder, all that we have left to do now, for real this time, this is actually the last thing, is use the validator to make sure that the container is properly set up. So we call dependency validator dot validate. We know this is going to return some data. Take advantage of VS Code to give us the explicit type of this data. And for the arguments of the validate function, we need the resolver, which is the container itself. We need the injector of that container, and we also need the objects and registrations dictionaries. Now we check if the data has found any missing dependencies. In theory, the count check should not be necessary, but let's do it just for safety. And if we did find any missing dependencies, we need to throw an exception. To print a nicely formatted error message for this, I'm going to create a new function called format missing dependencies. This is going to receive the dictionary of missing dependencies. And let's use string join here. So what's going on in this function here? By using the select function from link, this is essentially going to iterate through all the entries in this dictionary. For each entry, it will print the key, which in this case is the type. Then it will print the words missing. And then, by using the string join function on the value of the dictionary, and this value here is a list. So using the string join on a list will basically print every individual value of that list separated by a comma. So we print the type, and then we print the list of missing dependencies. And then if we take a look at the outer string join, it's going to print something like that on a separate line. And here all we have to do is call our format missing dependencies function and pass in the missing dependencies dictionary. And for circular dependencies, we'll do something almost identical, but instead of using a function that we called format missing dependencies, we'll implement a variant of it for circular dependencies, and we call that instead. And instead of separating things by a comma, let's actually separate it with a little arrow. Okay, and this is it. Now we have a fully functioning, quite robust, if I do say so myself, dependency injection framework that you can use in any C# project. In the next video of this series, we will cover a Unity-specific implementation making use of this framework that we just built. I hope to see you there, and goodbye for now.